Hey everybody, this is Mr. Parliament, and this video is going to walk you through a derivation of Gauss's law of gravitation. Now, as I've mentioned, we are going to skip our gravity and oscillations unit because it won't be covered on the AP test. But I wanted to spend today doing a little bit of a highlights reel of some of the stuff that I thought was particularly cool about specifically gravity, really. We'll look at one cool thing I have for oscillations as a Friday fact later on. And this thing that I want to look at about gravity is Gauss's law of gravitation. In order to derive Gauss's law of gravitation, we're going to deal with this hypothetical scenario that I've drawn out right here. We have a hole that's been drilled from the North Pole to the South Pole of the Earth. We have a skydiver who's jumping through it. And our question is, what is the force of gravity from the Earth on the skydiver at any point in time while they're falling? Now, if the skydiver was on the surface of the Earth, we'd find their force of gravity as 9.8 times their mass, and that's great for the surface of the Earth, but if we're very far away from the Earth, or on a different planet, or if we're partway through the Earth, the more general equation for gravity is that the force of gravity is equal to the gravitational constant times one mass times the other mass divided by the distance between them squared. Now, notice that this equation would give you the same value if we flip-flopped m1 and m2. So what that means is the force of gravity from this chunk of the Earth down here on the skydiver is the same as the force of gravity from the skydiver on that chunk of the Earth, which is consistent with Newton's third law. They're the same magnitude, but opposite in direction. So for this gravitational force, we know it's an attractive force between objects, so we can figure out what direction it is from the orientation of our objects. All right, so for this particular scenario, we're going to say that the skydiver is 1/3 of the way through the Earth. So from here on out, I'm going to start referring to the North Pole as the top of the Earth and the South Pole as the bottom of the Earth. And I'll call this direction up and this direction down. I know that doesn't make a whole lot of sense, but it'll just make it easier to discuss this problem as we go. So I'm going to call the distance from the center of the skydiver to the top of the Earth a height h, and call the distance from the center of the skydiver to the bottom of the Earth 2h, because we're 1/3 of the way through. You can see that I've drawn some cones coming off of the center of mass of the skydiver. And I tried my best to draw those cones with the same top angle for either cone. So if the top angle is the same, the base of the cone on the far side of the Earth, the South Pole, is going to make a bigger circle than on the near side of the Earth. So for this top circle, I said that that circle has a radius r and an area a. For the bottom circle, because the cone is twice the height, this circle should have twice the radius. You guys know that the area of a circle is pi r squared, so double r, you get an area that is 4 times the area of this circle. And for this derivation, we're going to treat these circles as really short cylinders, so very small h, very small height. So this cylinder right here, we're going to say has a mass of m. This cylinder right here would have a mass of 4m because its base is 4 times the area, and we're going to say that the heights of each of them is the same. So now we're going to calculate the gravitational attraction on our skydiver from either of those cylinders on either side of the Earth. So for the top cylinder, the force of gravity would be gravitational constant times the mass of that chunk times the mass of the skydiver divided by the distance from the center of the skydiver to the center of that circle squared. For the bottom circle, our force of gravity would be the gravitational constant times 4m times the mass of the skydiver divided by the distance between them squared. So 2h in parentheses squared is the same as 4 times h squared. We got a 4 in the numerator and a 4 in the denominator. They'd cancel out. And you can see that this equation for the force of gravity from the bottom circle is the same as this equation for the force of gravity from the top circle. And we can do that same thing for different circles all over the surface of the Earth. So if I go just straight left and right, those circles would be the same size. They would have a net gravitational force of 0. If I do it diagonally, I'd have one here, a larger circle over here on this side, and they would have a net gravitational force of 0 on our skydiver. And we can do that all over the surface of the Earth. And essentially, a thin shell of the Earth has a net gravitational force of 0. Now, these circles would, of course, overlap if we did that, but if we redid this derivation with a smaller angle of the cone, as that angle of the cone gets smaller, we would get closer and closer to an approximation of the surface of the Earth. All right, so a thin shell on the outer surface of the Earth has a net force of 0. We can also do the same thing a little bit further into the Earth. So this circle here, its gravitational force cancels out with this circle down here. This circle here cancels out with this circle here, and so on and so forth. So we have essentially from here to here, that shell of the Earth has a net gravitational force of 0. So I'm going to go ahead and draw what remains, what doesn't have a net gravitational force of 0. So I'm going to start at the center of the Earth, draw that circle right there. Let me just center it a bit. So this circle, and really I should say sphere, because we're dealing with a 3D Earth, this sphere is the only thing that has a net gravitational force on our skydiver. Clean this up, drawing up a little bit. And the reason why this sphere doesn't have anything canceling it out is if I drew a circle right here, the circle that would cancel it out would be out here in space. So there's no mass to cancel out the force of gravity from that circle. So this transcribed circle, starting at the center of the Earth to the center of the skydiver, that sphere in 3 dimensions, is the portion of the Earth's mass that has a net gravitational force on the skydiver. So as the skydiver gets closer and closer to the center of the Earth, that circle or that sphere gets smaller, and our net gravitational force gets smaller and smaller. And when our skydiver is at the center of the Earth, the net gravitational force is 0. And I think that makes intuitive sense because all of those different chunks of the Earth are pulling in different directions, and the net force is 0. So that's Gauss's law of gravitation. You might be familiar with Gauss's law in terms of charged objects. So if we have a charged sphere and you're inside of that sphere, the net effect from that charge is similarly all of the charge contained within a sphere from the center of the sphere to the center of the object inside of the sphere. So there's Gauss's law of gravitation. One application of Gauss's law of gravitation that I think is very interesting is there was a religious movement in the late 1800s known as the Koreshinity movement or faith, and they had a compound in Florida where they claimed to do experiments that they said proved that the Earth was a hollow sphere. So let's look at this idea of a spherical Earth in terms of Gauss's law of gravitation. So I've got this little person right here inside of a hollow Earth, and I'm going to draw a circle from the center of that hollow Earth to the center of our person. And the mass of the Earth inside of that transcribed sphere is the mass that has a net force on our person inside of the Earth. So obviously there's no mass inside of that transcribed portion since it's a hollow sphere. So the net gravitational force on this person is 0. They would be weightless inside of this hollow Earth. Well, you could make the argument that maybe this hollow Earth is rotating, just like our non-hollow Earth does, and therefore this person would be rotating with it, and they would try to move in a straight line, but the Earth is spinning underneath them and catching them and pushing them inward, and to them, there is an apparent outward force, an apparent centrifugal force that makes them think that there is a gravitational force on them. So that would work for at least parts of this hollow Earth, but remember that this is a sphere, so if it's rotating about this center axis right here, this person could walk out of the screen towards us, going up, closer and closer to this axis of rotation. If they were at the axis of rotation, they would be back to a apparent centrifugal force of 0, so weightlessness. So this hollow Earth would only really simulate close to Earth gravity on the equator, and as you walked closer to the poles of the hollow Earth, your gravitational force, or apparent gravitational force from that centrifugal force, would get smaller and smaller, eventually reaching 0. So given the fact that there's no point on the Earth that you can walk to where gravity just suddenly seems to go away, I'm pretty confident saying that the Earth is not a hollow sphere. So anyway, there's Gauss's law of gravitation. Let me know if you have any questions. You're welcome to email me. And have a great rest of your day. Thanks. Goodbye.